All right, so the thing about especially safer galaxies and quasars, um, and to some extent radio galaxies, although you're going to see there's some special things going on with radio galaxies, but it's really the core, the nucleus of these galaxies that is producing or where most of the energy is coming from. All right, so there's more energy coming from the core of these active galaxies than all the other stars. You can have hundreds of billions of stars combined. You're getting more energy out of this tiny little core that's maybe 20, 30 astronomical units in size. So this is something much smaller than a parsec. Right? I mean, this is an it's an incredible engine at the heart of these things. This is something else that I want everybody to understand. It's really important when we see variations, right? If something begins to vary, and it takes a certain amount of time for the variation to cross the surface of this object. The amount of time that it takes to cross the surface of the object is really a reflection of how big it is. All right, nothing that changes the amount of energy that's coming off of it. It takes time for that to happen, basically, because the speed of light is a constant in the universe. So this with the knowledge of how much time it takes these variations to take place, we can estimate what the size of the objects are. And they seem to be, as it says here, extremely small, right? So that, when we look at these galaxies, it's coming from the very heart of these galaxies, the nucleus, and a very small region of the nucleus. All right, so, and that should sound really familiar, by the way. All right, here's our first radio galaxy. Again, there's many of them. This particular one, I think this is Centaurus A, if I'm not mistaken. Anyhow, one of the characteristics, this is actually an unusual looking one. This one is looks like an elliptical galaxy and a spiral galaxy had a collision. And in fact, that's what we think happened with this particular galaxy long ago, and others like it. But this particular one, this is the thing that I really wanted you to see as far as radio galaxies, is you see these lobes that are perpendicular to the axis of the galaxy. In other words, they're following very strong north and south magnetic field lines, and they're away from the disk of the galaxy. And here's another, and of course, for a radio galaxy, most of the energy is coming out in the radio part of the spectrum. That's how it got its name, of course. But they look pretty much normal in the visible part of the spectrum. Here's another example where it's just showing these radio waves coming from this really concentrated at the core, at the center of these galaxies. Here's another one with the lobes, and it turns out that we think that it depends on the orientation of a particular galaxy as to whether we see these jets heading in our direction, or if we're looking at it from a perpendicular angle, we see these lobes, right? What we call radio lobes. So, in some sense, we think that this is whether there's radio lobes or whether we see the jets has to do with the angle that it happens to be oriented in the universe with respect to us, or I guess maybe how we're oriented in the universe with respect to them, right, which is basically the same thing. This is actually M87. This is a very famous active galaxy. It turns out that this is one of the nearest ones to us. And notice there's a jet of material. There's a blow up of that coming out, kind of almost exactly in our, not quite in our direction, but enough so that we can see the jet. And it is it interacts with the intergalactic material, intergalactic gas and dust. All right, so that was, again, just to reiterate, safer galaxies are spiral galaxies. Most of the energy is coming from the center. Radio galaxies, you do see a lot of energy coming from the center, but there's also these jets and tremendous amounts of radio energy. In fact, more energy is in these radio regions, in these jets, than like the rest of the galaxy, basically. And then we come to what are called quasars. In fact, quasars were discovered first. Quasars were studied back in the 1960s, and here's how they got their name. It comes from it's just kind of a short it's short for quasi-stellar object. So it's something that pretty much looks like a star, but it turns out that it has enormous, incredible redshifts. In other words, these things tend to be billions upon billions of light years away, right? And in fact, here we go. So there's you're having these incredible redshifts. And remember, I mentioned this before. There's a table. When you start to get redshifts this large, you need to use the table in, I think it's table 24.2, to translate the redshift into a distance, right? Because Hubble's law just breaks down basically when you start to approach the speed of light. When you get redshifts this much, where it seems like these quasars are moving faster than light. In fact, that became really confusing at first when people first started measuring these quasars. They didn't even recognize the most abundant element in the universe, which of course was hydrogen, right? You get these hydrogen absorption lines, but they were shifted so much to the red, and they're always shifted to the red, of course, and that's Hubble's redshift distance law, which really has to do with the fact that the universe is, it's kind of like the surface of a balloon where the balloon is being blown up. So when we go and we look at the light has been lengthened because the universe is blowing up, right? These are, of course, some of the common absorption lines. There's the H beta, H gamma, H delta, and they shifted over so much people didn't even recognize these at first. And then, of course, over some time they looked and they said, oh yeah, these are just really large shifts, incredible red shifts. All right, so and in fact, that's a better way to think of of this kind of stuff, is the red shift. That there's this, just a normal red shift. The recession velocity is really not the speed that these some of these galaxies inevitably will be heading in our direction, but that motion is completely washed out by the fact that the universe has expanded so much in the space between us and these galaxies that any actual motion of the star or the galaxy, I should say, is just completely wiped out. It's washed out, and so you're only seeing the expansion of the universe when you look at these things. All right, so quasars really do just look like stars. I mean, there's nothing. You look at this picture right here. The arrow is pointing at one of the quasars. Right? Nothing remarkable about it. Doesn't seem like it's anything special, but it turns out to be the most energetic things out there in the entire universe, these quasars. And there aren't any close ones. That's right. All the quasars are billions of light years away. All right, so let's see the redshifts in the look back. So if you definitely look at that table that's in our textbook to understand it. Let me go over this just a little bit. So if you were to just look at the redshifts, as we were seeing here, you would quickly see, when you look at, if you were just looking at the quasars, that they very quickly, after about 100 megaparsecs or so, the redshifts are showing recession velocities that start to approach the speed of light, and so you have to use the special theory of relativity, which, remember, never allows. Well, the universe, basically, it describes the universe. First of all, it's not Einstein's. I mean, Einstein just made the discovery that this is true, but it's the way that the universe responds to the speed of light. It makes the speed of light the same for all observers, and that includes these redshifts. All right, so here are some general properties and so let's talk about the engine. What is it that's causing this? And just to sum it up, by the way, it is these supermassive black holes, and not really. I mean, it's the fact that the supermassive black holes in the centers of these galaxies are there. Obviously, that's got to be there. But it's really the accretion disks. So it's very similar, for example, to when we saw like X-ray pulses that had to do with two stars that were binary stars that were orbiting each other, like within our galaxy, and one star is close enough to so the Roche, what we call the Roche lobes overlap, so some material can fall onto, especially if it's a dead star like a white dwarf, and that material can pile up, and there can be basically a nova, and you'll actually see X-ray emissions happening, and you see that even with some neutron stars. So this is basically the same scenario, but on steroids, right? Because you're talking about incredible masses. When we look at these supermassive black holes, and these are supermassive black holes well beyond the black holes in the center of our galaxy, or the black hole, the supermassive black hole in the center of the Milky Way, which of course is 4 million times the mass of the sun. With these active galaxies, you're talking about billions of times the mass of the sun. All right, so here are some of the things. You have extreme luminosity, so it's approaching anywhere from 10 to the 37th to 10 to the 40th watts. Sometimes even a little bit more. You get non-stellar energy that is concentrated in a little tiny region. Of course, it's the nucleus of these galaxies. How do we know that it's really tiny? Because it just takes a small amount of time for the variation to take place, right? If it was a larger object, the variation would simply take longer, because of course the speed of light is a finite value. And some of them exhibit jets and even explosive activity they actually look like these things just exploded. And you also see really broad emission lines, which of course always means something's rotating really fast. All right, so here's an example of this is basically our model of what's going on with these active galaxies. So in the heart of the galaxy, there is a supermassive black hole, which of course has an accretion disk around it. And there's of course always a magnetic field that's associated with that. And when charged particles, when a charged particle, electrons or protons, encounter moving charged particles encounter a magnetic field, they will swirl around. They'll make like little circles around the magnetic field lines, and